gets into the cell, right? How it unpacks, how both of the two types of retrovirus that we're seeing now, how they enter the nucleus, right? Coronavirus is going to wait for the cell to replicate, while lentivirus is going to use nuclear proteins to get inside. And then how they proceed on the replication of their genome. How they integrate to the genome, that's what we saw, right? How they integrate. We also saw how they make the complementary DNA, the positive and the negative sense DNA, correct? And how, after integrating, they produce messenger RNAs that can either be packed inside of a capsid and get out of the cell, or can be spliced and read in different ways to produce different proteins so the virus can continue to survive inside of the cell. So it's kind of like the retrovirus is a constant state of latency. That's the way they divide, is through latency, right? It's going to be inside of the cell, no matter what, right? Otherwise, it cannot duplicate, it cannot replicate. And there is no exponential replication. So, reminding you of that, now we change the focus to see how would the retrovirus induce cell transformation. Because the retrovirus is going to need to do one thing. What is that? What do you think the retrovirus is going to need to do in order to increase its fitness? Make the cell divide, right? It is dependable, it is depending, good job, it's depending upon the cell to continue dividing so it can divide with it. Of course, some kinds of virus, such as the lentivirus, like the HIV, is capable of producing RNAs that are going to be kept inside the capsid and sent out, so it can increase its fitness that way. But would not be wonderful for the HIV virus if the cell continued replicating, right? Because then it's not only depending on sending virus out, bud off virus, the amount of virus bud off of the cell, but it's also going to multiply as the cell divides. Okay, so let's see what the virus does in order to modulate this kind of division. So through integration of near oncogenes, or let me put it better, those are not oncogenes until they produce cancer, right? They're proto-oncogenes, genes that if you mess with, you're likely to end up with a cancer cells. What kind of genes are those? What they control? So proliferation, what else? The checkpoints, right? So specifically, they control cell proliferation because they control the checkpoints. Let me tell people that have not gone through by 110 yet, what in the world is checkpoints? So checkpoints are places during the life of the cell that the cell will check to see if it's okay to proceed. Let me give you an example. Before the cell in interphase, which is prior the end phase, the cell duplicates its DNA and has all that trouble to make a copy of every single chromosome when we have 46, right? Before doing so, it will check, is the environment safe? Can I stop everything else that I'm doing? Because at that point, not much transcription is going to take place. Not many proteins are going to be produced. You're going to have many replication bubbles. The DNA is going to be pulled apart. The nucleus is going to disappear. The nuclear envelope is going to disappear. So before going through all that trouble, do I have enough nutrition in the cell? Is the environment safe? That's a checkpoint. Another checkpoint is before entering M phase, and that is on G2 phase. And in G2, the cell may ask, did I replicate all the DNA correctly? Is all mistakes being repaired? Is there any DNA damage yet? Because you don't want to enter into a division and produce a cell that's not exactly like the mother cell. I want all the cells of my fingers to be the same. I don't want to grow an eye in here. Right? So, therefore, that question is also important. The last checkpoint is on anaphase, when the chromosomes are separated. This is very important, especially in meiosis. When the chromosomes are separating, the kinetochores are holding the two copies, the two sister chromatids together. You're supposed to disconnect those copies, correct? The mitotic fuse is supposed to grab both sides very well. Why? Because I want to end up with the same number of chromosomes in cell A that I want on cell B. If the kinetochore is put together so tight that they cannot be separated, or if the mitotic fuse is not grabbing the kinetochore properly, we can end up with one cell with more than one chromosome than the other. And if this is meiosis, I can end up with one gamete with 22 chromosomes and another gamete with 24. That's the case of that can cause many diseases. It can cause Down syndrome. It can cause triple X chromosome disorder, Klinefelter disorder, and so on and so forth. So those checkpoints are essential. So proto-oncogenes that controls proliferation will control different kinds of enzymes and proteins that controls those checkpoints. But there is another class of proto-oncogenes besides of the one that controls proliferation. What is that? Besides of genes that control proliferation, what are other kinds of genes that, if messed up, can end up in cancer? Say one time. Tumor suppressor genes. And what are those exactly? You don't need to answer. That's someone else. What's tumor suppressor genes? What are they controlling? Because we hear about, I'm sure all of you have heard of tumor suppressor genes, right? But what are they? What are they controlling? Say again? Overgrowth. So they're in the first category that we just talked about as well. But what are the other two categories that I'm trying to get from you? There are also tumor suppressor genes in there. So what's a cancer cell, guys? How many of you have taken bioattend? So you should know. Cell death, apoptosis. So a cancer cell is a cell that doesn't stop divide, is a cell that doesn't die. So apoptotic genes are also, you also have tumor suppressor genes that are apoptotic genes. If the answer is no, the damage cannot be repaired, then we must proceed into apoptosis, correct? The damage is too large. Before in G2 phase, if that checkpoint, the answer is no, we must proceed into apoptosis. What else? A cancer cell is a cell that doesn't stop growing and is a cell that doesn't die. What else? What's another characteristic of a cancer cell? Talk to each other. So the guys stop cutting the grass right over the door of my classroom.
Did she mention that? I think so, right? It divides and we die. You can stay down
Yeah, I can.
Kind of say like pseudo for quite a bit.
Okay, cell that doesn't die, a cell that doesn't stop dividing. What else? Chris? Yes, and what that leads to, what happens to that cell? They do, but I wanted to get like the general result. A cell still nutrients, it's right? Because you have quite a bit of musculature growing around. But what happens to that cell that steals the nutrients? Yeah, what happens to that cell? Well, sure, it doesn't, yes, it does survive, you're right. But it doesn't, think about it. Think about it. If I keep eating and eating, which I do, keep eating and eating and eating and eating, what's going to happen? Growth. In my case, it would be to the sides, right? Not up, unfortunately. So, a cancer cell is a cell that doesn't die, doesn't stop dividing, and it grows, it grows, it grows, it grows. So, proto-oncogenes are genes, that will control cell death, cell proliferation, and cell growth. We have tumor suppressor genes that are enzymes that are supposed to suppress all those characteristics, right? To control genes that will push the cell into death, genes that will make the cell stop dividing, and genes that will make the cell stop growing. Yes? We're going to have genes that are going to make the cell stop dividing, stop growing, and dying. Makes the cell to die. Those are tumor suppressor genes. Together with the genes that controls cell death, cell proliferation, and cell growth, those genes are referred as proto-oncogenes, genes likely to cause cancer if mutations accumulate. Now, retrovirus promoters directs abnormal expression of cellular oncogenes. And they do that evolutionary purposefully. Why is that? Why it's advantageous for retrovirus promoters to abnormally enhance oncogenes. What is evolutionary? Why they were selected that way? For variation? No, not for variation. Why they are promoters? Why do they get implanted beside oncogenes? David. Yeah. So if you go ahead and mess up those oncogenes, right, you're likely to the cell to become a cancer cell, and a cancer cell is the dream of a virus. Because a cancer cell doesn't die, a cancer cell divides non-stop, right? And the cancer cell doesn't stop growing. So it gets tons of nutrients. So it's wonderful for the virus. It is a perfect state for latency. It will stay there forever. So suppressor elements for an oncogene or repressors is disrupted. So we do not only insert the retrovirus right beside a oncogene, like a gene that controls apoptosis or cell proliferation or those checkpoints, but we also mess up the tumor suppressor genes. So we bombard the cell from two different fronts, right? We kill the cell's defenses for cancer, which is tumor suppressor genes, and we go ahead and enhance oncogenes, proto-oncogenes. Are we getting this? Any questions? No? Are we good? I will ask multiple choices on this. I'm making multiple choices today. Okay? Make notes. All right. So transformation by stimulating growth of neighboring cells. What's another dream come true for a virus? Not only to be able to stay on a cell forever, in a cell that keeps dividing, correct? And reproduce vertically from the mother cell to the daughter cell, but also to be able to infect all the neighbor cells laterally. And this is what it does. Retrovirus integrations leads to the increased production of cytokines in response to viral gene expression. So now the virus is capable of telling the neighbor cells, like a bad friend, turn bad too. Hey, why don't you turn into a cancer cell? Look at this, it's good for you. So that's also going on. And that's one of the characteristics of cancer cells. Cancer cells that are malignant are capable of influencing the next door cell to turn into cancerous cells as well. Continued overexpression of cytokine can lead to changes in T cells and leading to cancer. So now it's not only the cell that's being infected with the virus, but the next door cell as well. Because if the next door cell keeps dividing, right? It's wonderful. Then we have more cancer cells to infect. All right. So revision from Bio 110 for people who here has not taken Bio 110 yet, or taking right now. Have you got to this point already? Good. All right. So what happens right here is a signal pathway, correct? So we have a signal molecule that will bind to a receptor tyrosine kinase. Then those two molecules will dimerize. When they dimerize, they're capable to phosphorylate each other, autophosphorylation. Once that happens, notice that different portions gets phosphorylated, right? And those phosphorylations are docking points for other molecules. Depending on which kind of phosphorylation, different molecules will be able to dock. When I teach Bio 110, I like to ask the question of, if you phosphorylate here, what happens? How about if you phosphorylate here? How about different combinations, what happens? So now, in this case, we have an adapter protein, which is GRB, right? And this GRB protein is going to allow the RAS activating protein, SOS, to dock in. Remember that RAS is a monometic G protein. And then, what's going to happen? What's going to happen is that this G protein is going to release the GDP, and GTP is going to hop in. So when GTP hops in, this RAS monometic protein is activated. Why is this important? Because this RAS protein right here is going to serve as a secondary messenger that's going to usually activate, as you're going to see on the next slide or so, cyclic AMP, which is capable of amplifying the signal. That's what you learned. Remember? You have signal amplification. And when you have signal amplification, you're capable of turning on different kinds of proteins, and you form a signal cascade. In this case, we have RAF. You have RAF that activates MAC, which then activates ERK by putting a second phosphate on. And then ERT, which is MAP kinase, is capable of creating different kinds of expression. We can create different expressions by activating protein X, protein Y, gene regulatory protein A, gene regulatory protein B, and we can end up with change in protein activity or change in gene expression. That's all the virus wants, change in gene expression. The virus wants to change the genes that control cell proliferation, cell death, and cell growth. Yes? Okay. So let's see how we end up with the tumor. So in the normal epithelium, we have a tumor suppressor gene that may be lost. So this is attacking the cell in one front. We are killing the defenses from cancer. And an example of that is APC. APC, when it accumulates mutations, then the suppressor of the tumor is going to be out of the window, gone. Then we have tumor accumulation on the gene that codes and is expressed as RAS. If you have a mutation in here, maybe RAS can no longer be activated, or maybe RAS is activated all the time. What happens if the RAS is activated all the time? So we have gene expression going on at all times. This is exactly what the virus does. It's turned on all the time. You cannot turn it off because GTP binds to the RAS and doesn't leave. There is never an exchange between GTP to GDP. Okay, it's a constitutional mutation. Then maybe because the genes are being pushed at all times that the cell is multiplying, we have another tumor suppressor gene loss, larger tumor. So now we're growing non-stop. First we're reproducing non-stop. Now we're growing non-stop. Then a third tumor suppressor gene, such as p53. And if p53 is lost, what happens again? What is p53? Take the spider webs out of your thing. Right? What's p53? It controls, yes, cell growth, but what did it prevent really? It controls apoptosis too, but exactly what it does. It does too. It does all the above. All the above is correct. Yes, all the above. Specifically, what did it does? Of course, if I would ask that multiple choice, I would not put all those answers. Say again? Yes, it has to do with CDKs. CDKs and cyclins, remember that? So p53, what it does, it codes for a protein that is capable of activating p21. And p21 is the clamp that holds CDK and cyclin together and prevents them to be active and to push the cell into mitosis until damage to the DNA is repaired. Yes? So it works on that checkpoint after G2 phase. So you're going to have G1, S phase, G2. On G2, the checkpoint is all the damage of the DNA repaired. then we hold on N-CDK and N-cycline until we're sure that that damage is repaired. Because we don't want, again, an eye on the finger. Okay. So we lose that too. So now the DNA is further damaged. The DNA that's damaged is not repaired anymore. Then we have a tumor that becomes invasive. Dr. Pallavicini, which was our previous dean of natural science, that taught the class of cancer to me when I was here. She is a world-known specialist in cancer. She used to say that in order for a cell to become cancerous, you need an accumulation of 6 mutations on proto-oncogenes. So you can count 1, 2, 3, 4 mutations. You have an invasive tumor. All right, let's see the job of our viruses. So the virus here, what it is doing, it is disrupting this whole system. You notice that here we might have RTK, a receptor tyrosine kinase, okay? Here we have a signal, right? Remember that I said that the virus, besides of wanting to implant themselves right close to the promoters of proto-oncogenes, it also likes to ramp it up, the production of cytokines to make the neighbor cells bad as well. So we have growth factors that will let the next door cells to know, oh, you need to divide. This is very important, and this is part of an endogenous mechanism. Why? Because if I have a cut on my hand, I want the cells that are still there to let the next door cell know they need to divide to close the cut. Yes? Makes sense. So you can notice in here that we have protein kinases that are going to be like MAC, like ERK, that are going to be phosphorylated. In this case, it's a CSRC family of proteins. And this protein that's phosphorylated, which is part of one of those MAC kinase families, are going to travel inside the nucleus, and it's going to stimulate cell division. And it's going to create a signal that's an apoptotic signal. In another hand, I might have another mechanism right here where I have G protein, right, disassociating between alpha subunit and beta and gamma subunit, and the alpha subunit in another hand activating a second messenger, which is cyclic AMP, in abundance, which will also travel through the nucleus and create the same kind of response. Antapoptotic signal, cell division signal. Notice that P53 was going to halt all this division until we are sure all damage is repaired. This is the way things are supposed to be. Now let's see when virus is around on the next door cell, what happens. When virus is around on the next door cell, what can happen is this. Notice that here is our protein that's supposed to be phosphorylated, correct? All right. Now we have a signal, a cytokine signal, that is going to bind to the receptor tyrosine kinase that's going to ramp it up, this phosphorylation. So this phosphorylation of this MAP kinase is going to happen more often. Number two, we also have signal coming from another kind of receptor tyrosine kinase. We have EGFR kind of signal ramping up. So now we're having signal from two different sources. So we have lots and lots of CSRC protein, MAP kinase proteins that are going to travel through the nucleus and push cell division to happen. In another hand, remember that I said we bombard the cell to two different fronts? Another hand, now I have RAS, right, the monometic G protein that we just saw, bound to GTP at all times. We have a constitutive mutation here. And then RAS is going to continue ramping up the levels of cyclic AMP to the max. And now, push out as well cell division and apoptotic signal is going, the volume is going to turn up. And then on the other hand, we have TAG, this protein that inhibits p53. And by inhibiting p53, we inhibit p21. And by doing so, we're going to enter into mitosis no matter what. If DNA is damaged, if the DNA has to be repaired, doesn't matter. We're still going to enter. And therefore, this cell is going to turn into a cancer cells as well. Any questions? Yes, yes, yes. And this works, this constitutive mutation only works because we're having cell division already, non-stop. But remember that before that happens, we also have cytokines, because this drawing is not showing, we have cytokines binding to another receptor tyrosine kinase. We have also signal molecules from the next door virus, next door cell, binding to receptor tyrosine kinases and stimulating this whole process. So the cell is dividing until it comes to the point that it begets a mutation on the RAS protein itself. Okay. All right. So this is also from Bio-10. This is also an example of constitutive mutations that might happen because the cell is dividing so much. DNA polymerase is really good, right, to not make so many mistakes. And also DNA polymerase 3 has the ability to come back and perforate. However, it does mistakes. 1 out of 10 to the 9, but it does. And more division, more probability to have mistakes. It's like someone telling you that you're more likely to get into an accident close to your house. Of course, you drive there the most, so your probability is higher. So, as you can see here, small mutations, these point mutations, a valine changing to a glycine. This can lead to a mutation on this particular receptor, right? And then you can have